Okay, so in this example, we will be analyzing something called a rotating cylinder viscometer. And as you may already know, viscometers are used to measure the fluid viscosity. And because there are no direct methods to measure the fluid viscosity, like we can measure the mass of the fluid by directly weighing it, but we cannot use any such direct methods to measure the fluid viscosity. So we need to employ indirect methods in such a way that we basically there is a moving part or rotating part which comes into contact with the fluid, and because of that there are velocity gradients and shear stresses acting on the moving part, and then we can measure the torque or the force acting on the rotating or moving part, which is basically due to the presence of fluid and the viscous stresses, and then we can correlate the measured force or torque with the viscosity, thus calculating the viscosity. And in this example, we have a rotating cylinder. So the construction is simple. There is a hollow shell, and we insert a big cylinder inside that shell, and we fill the gap between the middle cylinder and the hollow shell by the fluid, uh, for which we want to measure the viscosity, and then we rotate the middle cylinder with a known angular velocity omega and measure the torque acting on it. And from there, by using the analysis that this problem is asking us to derive, we can find out the viscosity. So if you look closely, the fluid is in contact with this inner cylinder along its circumference, which is here, uh, and along the bottom circular area, which is shown by the green line here. So, so to find out the torque, we first, so we know that torque is R cross F, where is the force. So to find out the torque, we need to first find out the forces acting on the cylinder at different locations. So we can divide the forces acting, the total force acting on the cylinder into two parts. One is the force which is acting on the circumference, which is given by blue. So I'll just use the blue color here as well. And the force that is acting on the bottom, which is shown in green color. So similarly, total torque will be the torque which is acting on the surface area of the cylinder, shown in blue, and the torque acting on the bottom circular area of the cylinder, which is shown in green. So yeah, let's start with the force acting on the circumference. So since this is cylinder, it is useful to write everything in cylindrical coordinates. So we have a radial coordinate r, then polar coordinate theta, and the vertical coordinate as y shown there. So if you look at this device from the top, so the top view reveals that there is this inner cylinder and the outer cylinder. So the inner cylinder is rotating with an angular velocity omega, and the outer cylinder is stationary. So because of the no slip boundary condition, the fluid which is close to this inner cylinder is moving with a velocity omega r, while the fluid which is here at the outer cylinder is not moving and has a zero velocity. So the fluid in between, the fluid velocity in between varies linearly from 0 to 0 to omega r, and then basically the force that is acting on the inner cylinder is the viscous shear stress due to the velocity gradient in the fluid here. So let's just first find out the velocity gradient. So here basically this is the direction r and this is the direction theta. So here the velocity gradient is du theta by dr, that is the theta direction velocity changing with the r coordinate. And since the thickness of this gap is t is very small compared to the radius, we can assume the fluid flow to be linear inside that narrow gap. So this gradient comes out to be 0 minus r omega upon r plus t minus r. So this is the velocity at the outer cylinder, and this is the radius of the outer cylinder. This is the velocity at the inner cylinder and radius of the inner cylinder. This comes out to be minus r omega by t. Now uh, the force acting on a small circumferential area will be the shear stress acting on the circumference multiplied by 2 pi r dy. So this is your inner cylinder, this is the outer cylinder, and at a particular height y, we are choosing this strip, uh, radial, the circumferential strip of thickness dy. So its area is 2 pi capital R into dy. So this is basically mu times d u theta by dr at the circumference multiplied by the same area 2 pi r dy. So substituting this in here, we get df to be equal to minus mu r omega t into 2 pi r dy. So the total force can be obtained by just integrating these small forces acting on small area elements. So after integrating this term for y ranging from 0 to h, which is the height of the cylinder, we'll find out that f circumference is minus mu times r square 2 pi omega divided by t into h. But we want to find out the torque. So, so the torque on the circumference is basically the small torque acting on the small element is capital R multiplied by TF circumference. So the total torque is the integration of the right hand side from y ranging from 0 to h r multiplied by minus mu r omega by t 2 pi r dy. So if you solve this, you'll get this to be equal to 2 pi mu r cube. So there is this negative sign here, and that just tells us that this torque is acting in the opposite direction to the direction of rotation. So yeah, so this is the torque acting on the circumference of the cylinder, but we also need to calculate the torque acting on the bottom to find out the total torque. So now if you uh, look at the bottom from the side, what you will find out is that this is the bottom surface of the inner cylinder. This is the bottom surface of the outer cylinder. This is radius r, and the fluid here is moving with a velocity omega times r. So r is the distance of that point from the center, and the fluid here at the bottom is not moving. So again, because this gap is very thin, we have the velocity uh, as a linear function of the height y. So if you look at this from top, this is basically inner cylinder with a radius r, and since this is moving, angular velocity omega. Let's say we are looking at this small strip at a distance small r from the center, thickness dr. This is what the fluid velocity looks like there. So again, the velocity gradient du by dy at the bottom is r omega minus 0 divided by t minus 0, which is simply r omega by t. And similarly, the force acting on this small element here is nothing but the shear stress acting on that small element multiplied by its area, which is 2 pi r dr in this case in polar coordinates. So this is simply mu times du theta by dy to 2 pi r dr. So the torque acting on this small element will be simply r times the force, and if you substitute this here, you'll get this to be equal to r mu times r omega by t multiplied by 2 pi r dr. So to find the total torque acting on the bottom surface, we just need to integrate on both sides. So T bottom is integrate from r equal to 0 to r equal to capital R mu omega t. So if you solve this, you'll find out that this term comes out to be 2 pi by 2 mu raised to 4 omega by t. So again, remember, this torque is basically trying to oppose the motion of the rotational motion of the disk. So the torque is acting in the opposite direction to the motion of the disk. So there will be a minus sign here because it is acting on in the opposite direction. So if we just take the magnitude of the torque acting on the bottom and the torque acting on the circumference, the total torque comes out to be which is equal to 2 pi mu. I'm giving you a simplified form of this addition. And so this is the circumferential part, and this is the torque on the bottom. Yeah, so that is the expression for total torque. Now, as you can see, if we just measure the torque acting on the inner cylinder, we are rotating it with a constant velocity omega. The radius is also fixed. The thickness of the fluid film can be measured, and also height of the cylinder and radius again are fixed. So everything here is fixed except the dynamic viscosity. So if we measure the torque, we can find out the dynamic viscosity of the fluid. So yeah, so that's it in this problem.